So, hello everyone again. My name is Marika, and I will be the moderator of today's meetup. So, first of all, I want to welcome everyone. Thank you for joining us. Today, we will listen for a technical talk, image recognition for tracking small and fast-moving objects by our colleague Simon Calabrese, Big Data and AI Platform Architect. But before we start, I want to tell some rules of the meetup. So first of all, everyone who is online now, you can ask the question during the talk. Please write them in the chat and check that you will be muted during the report, not to distract our speaker and distract other participants. All questions will be answered in the end. So please wait and just check that your questions are visible for everyone in the chat. Also, please check the muted microphone. It's very important and crucial. And for now, I will give the word to our colleague Roman to tell more about our company, and after that, tell more about presentation too. So, Roman, you can start, I think.
Yeah, thank you, Marika. Am I audible? Can you hear me well?
Yes, everything is
okay. Fantastic. So, hello everyone. Welcome to Grid Dynamics. My name is Roman. My role is very short. I'm the location lead here in Krakow. And my second role is our technology practice manager for the AI practice. So I'm somehow related to what Simon will be talking about today. I will tell a few words about the company, but before I do so, I'll ask the audience, how many of you know something about grid dynamics? Okay, good. Employees do not count. And out of all our guests, are you here for the first time or not? Can you raise your hands? First time? Okay, that's cool. So we have some new people there. Nice to see all of you guys. So I will be brief, but probably it's going to be useful for those of you who are here for the first time. So about Grid Dynamics, first of all, we are the IT services company. So we are building the software for large enterprises primarily. We do have some small clients, but primarily we are building the software for Fortune 1000 and Global 2000 companies. So these are one of the largest companies in the world. I'm sure all of you know what the IT services means. So I will jump directly to the geography on who we are and where we are. We are probably not the largest ones. We are not EPAMs or Luxoft at this point, but we probably get there. We want to be there. Right now, we are 4,500 people company. We are very diverse in terms of where we are based. So in Poland, we probably have the largest location country-wise. So we have around 1,000 people in Poland, and here 450-ish people in Krakow. So we have a pretty large presence here in this office. But you see our headquarters, our main headquarters of Grid Dynamics Holdings in the San Francisco and Bay Area. It's been there for all times. Our European headquarters are in Zug in Switzerland, and we also have very large presence in terms of our engineering offices in India, in Europe. And Jamaica is also not a joke. We have a real office with real engineers working out of Jamaica, and Mexico and Argentina. So we are very much present in Latin America as well. Moving on. About our customers, I think our customers speak the best about Grid Dynamics. So I'm selling a little bit the company, but our clients tell the best, and the clients who are here is usually not just a few projects. These are very large projects and many people working on them. And you see that the logos of Apple and Google here, they are for a purpose. They are very large customers of ours, I mean, relatively to our size. Pepsi's, Tesla, Shimano, so many logos you see here, and I'll be naming. You can see them. It's on the slide, but all of these companies are our clients. So whoever works in Grid Dynamics have a good chance working for the clients. Except for Google, by the way, is not just our customer. You see that we have a whole number of partners that we partner with, and Google is also one of our large partners. So we are delivering the projects together with Google, as well as building software for Google. But obviously, we are working with other hyperscalers, so Amazon's, Microsoft's, and again, not going to be reading through all of this list. That's for a reference, but we are working very, very heavily with our partners to deliver the projects. Somewhere we are getting the new business from them, somewhere we are leveraging the partners to deliver the software. But this is a very, very large operation that we have with our partnership teams. We are very serious in a way how we treat our people. So community of practice is on this slide for a purpose. We are very, very diverse in a way on what kind of engineers we have in the company. So obviously Sign is a great representation of our AI and big data practices, but we're also doing the DevOps, mobile, key automation, business and system analysis. Obviously we have a huge management community because we need them to deliver the projects, not just for fun, back end, front end. So we have lots and lots of processes that we built around communities of practice. I will tell a few words about how we treat our engineers. So it's going to be useful for you because, again, this is something that represents our company very well. This is the usual slide on how we treat our engineers in terms of the levels. So obviously we start from the 0 level and we go all the way up for the technical grades to the level 7. And worth mentioning that all our engineers, they have a chance to, at some point of time, to switch their track. They may go to architects like Simon, they might go to management like myself. So I've also been on this technical path at some point of time. But obviously there is a chance to stay at the technical path and grow all the way up to the very last level 7. Unicorn, yeah. He's saying unicorn. This is a slightly overloaded slide, but I intentionally left it today because there are a few things I want to talk about. So very important thing that as a whole and probably this is a part of culture of Grid Dynamics that's been here for many, many years. We've been founded in 2006. So we've been here on the market for quite a long time. We are usually hiring the top 10% of the market. So we are looking for the best engineers. And at the same time, we are investing very heavily in the internship programs. So if you have friends that would like to become an intern and get to the IT, this is a great chance. And we are making lots of things that we built around the development of this engineer, starting from their level 0, where they interns and then grow all the way up. And this circle here, it actually represents all of these activities that we are doing together with the engineers. And engineers are actually the primary contributors in all that activities. Just to name a few, Dynamic Talks is probably, that's what we have today. So this is a usual practice, and this is happening all around the globe, not just in Krakow, in Poland, everywhere. We have the Grid Lab, so we have our R&D department, and there are lots of work being done within the R&D. We have our Grid University, and some of the people here, they are also representing our Grid University, and this is the full-blown school that educates not just the interns, but there are development plans for all profiles and all seniority levels. So we are trying to bring and get the best out of our engineers and give them an opportunity to grow. And we also have the boot camps for the architects and technology practices that are built around the offerings that we deliver to our clients. So all of these things is built around our engineers and the delivery that they're doing for the clients. So lots of processes, and for sure it's lots of fun within the firm. Just a few numbers about what is happening today. So we have the Dynamics Talks, and these are just the numbers. So you can see that we have lots of partners. It's not just ourselves that are doing this. Today it's our own Dynamic Talks. Sometimes we do this with the customers. Hundreds of speakers, basically tens of thousands of attendees. And venues, again, you see 38 venues. Sometimes we do Dynamics Talks here in our offices. Sometimes it's not just the offices, but it might be the venues of our partners as well. So this is something that this is actually a very good brand of ours that's it. So, well, obviously join us whoever wants. So this is part of the marketing thing. Find opportunity in your area. So the barcode for our careers opportunities. We do have our recruitment representatives here today. So whoever wants to know more about our open positions, please scan or go ahead, and our recruitment folks will tell you about the opportunities. And obviously follow us on LinkedIn. We will be, all of our events, they are marketed there. So you'll get an opportunity to get the news out of that page. On this note, I will give this over to our AI and big data architect Simon with his speech. So it's going to be more technical than my speech for sure. But I hope that you'll get fun. So thank you.
All right. Okay. Test. Everybody can hear me? I guess so. Okay. All right. So welcome anyone. This is actually a presentation that have been already presented in the Data Science Summit just a few weeks ago. The reason why we decided to make it also as a grid dynamics talk is because we wanted to have a more broad knowledge sharing, especially with the people that are in Krakow and not in Warsaw that had possibility to attend there without basically our partner. So what we'll be talking about today. So Florence-2 and SAM-2 are two deep learning models, one deployed by Microsoft, one deployed by Meta, and they are pretty used for computer vision and in case of Florence, also more. So in my case, I'm going to talk about it in scope of tracking small and fast moving objects. And based on that, I will be introducing a bit more about myself. So as mentioned, I'm a big data and AI platform architect here in Grid Dynamics. I perform a lot of artificial intelligence related R&Ds and also working on pre-sales for our clients where I basically propose what we have as a blueprint, what we evaluate, and what we used in our previous experiences in order then to, first of all, accelerate the delivery of them, but also in order to get some insights so we can get our blueprints always up to date and at the same time have it more efficiency when we go over to another project or a new existing one. Apart from that, I'm also a football player and I'm passionate about racing sports. That's why we have these main topics here covered today. The reason why I decided to elaborate these two models is because these two cases, so sports, especially football, or as for our US audience, soccer and tennis or other sports that require a fast moving ball, is a main challenge to track. And there are a lot of discussions about it in terms of accuracy versus data loss versus portability and so on. Racing sports is one of my passion, and at the same time, you can imagine that nowadays motors like Formula One or MotoGP, our bolids are really fast, really fast engines and fast vehicles. Okay, so I will not spend a lot of time here on the agenda. I will go over it, but in general, there will be an introduction of object detection and segmentation for who is not familiar with it. For who is familiar with, feel welcome to ask more questions if I say something that you might disagree on. Okay, so applications of the products. Yes, sure. No, I will have a QA session at the end. Okay, so where we can apply these two models, but in general, object detection and segmentations. So we can see robotics, data capturing, autonomous vehicles, surveillance, data analytics, and augmented reality. I put the first three on the line because it's a field where, in our case, in Grid Dynamics, we are trying to expand, especially when it comes now to this boom of AI. Robotics is also getting a lot of importance, a lot of popularity. And in order to apply this, you need to have a lot of these other products combined to the hardware. So in our case, what is the problem? So here we can see we have two motorbikes. One is relatively small, relatively slow, and one is really fast. So what is the challenge here? First of all, the camera is stable, so it doesn't move. And the motorbikes, you can see that changed the perspective. So we started with a motorbike that was taken horizontally, and then moving forward, it changed the shape. So if you put this problem in maybe 2 decades ago, you need to have a model that is trained on multiple perspective of the same object, and also different color, different light, and so on and so forth. So moving forward, where object detection and segmentations are involved in this scenario. So object detection stands for identify, classify, and track an object within an image or a series of images. Segmentation enhances this detection, applying a pixel level object identification, instant segmentation, scene understanding, that is one important topic, especially in terms of Florence-2, and semantic segmentation. What is semantic segmentation? Is basically you can give not only the video or the photo, but you can also add some prompt on top of it in order to have more accurate answer. But here we started with the challenge. So there are a lot of tools, a lot of products, models that you can find online, but every model, every product has some positive and some negative points to consider. So these are common in our circles. You can see the common issues, common challenges that you face when you have object detection and segmentation models. So as I mentioned, in the motorbike, you can have deformation, illumination, fast motion, and re-identification. About re-identification, I will go later on more in detail, but for example, for deformation and fast motion, we noticed that, for example, the motorbike was changing, and for illumination, it can be imagined during like a Formula 1 race. You can start like when you pass next to the stands, you can have the shadow, and then suddenly you are outside of it, and there is a light that is really bright and can change the color of an object. So the car is a simple example that you can fix, but imagine it during, for example, a football game where the ball has different shades, different colors, and then with the light reflecting on it will be like bright white, and maybe in the shade you can see that there are some red stripes or the stars in case of Champions League and so on. So in this case, what happened? The ball might be confused with, for example, the penalty disc. That can be one usual scenario that can happen. On the bottom, we can see three main issues that are happening nowadays. As I mentioned, you can also take really big VLLM models, like, for example, Llama Vision 13, or you can take even bigger ones, like if you want to deploy some open source models instead of using, for example, ChatGPT or OpenAI models. So in this case, you need to, especially in terms of robotics or edge devices, you need to have something that is lightweight. So something that can be placed in an hardware that maybe everyone can access, but at the same time can be even an enterprise that don't want to spend millions on having a really strong GPU to run your model on. So you need to find one model that can cover, first of all, multiple scenarios. For example, can be OCR, can be object detection, can be even capturing and so on. But as I said, you have to consider performances over resources and portability. The point in the middle is a crucial point, especially when it comes to Florence, because Florence-2, like also SAM, but especially Florence, comes with two different sizes, the base and the large. The large can run perfectly on a GPU-based device, but the base, for example, can perform really well even on a simple CPU device. So in this case, you can have a pretty good level of accuracy also for a CPU-based engine. Portability, as I mentioned, is mostly for edge devices, security cameras, IoT, and so on. Okay, so conceptual workflow. Here, there is nothing in detail than what is expected when you want to interact with this kind of models. So on top, you can see a synchronous job. So let's imagine that you want mostly to analyze an image. So I don't know, you want to apply something in terms of, I mentioned one of our clients, for example, for clothing. You want to get some cloth and you want to, for example, extract the t-shirt from a photo that is a model with a nice polo color green. And then you say like, okay, what if this polo want to be a t-shirt and I want it to be red? So in this case, you can identify the t-shirt, you can segment it, and you can also use it in order to, for example, find something based on your input. So you say, identify the t-shirt, make it green, make it like a polo t-shirt, and so on. This can be synchronous. It's really instant. You can wait. But let's imagine about a video clip, a video that, especially nowadays, can be 4K, can be even full HD. I think is the basics right now if you want to have a certain level of accuracy. In this case, it will be quite complex with nowadays hardware to say like, okay, I upload a video, boom, done. After 1 second, 10 seconds, you have everything in place. Because you need to consider that every frame is basically a matrix. So for 1920 times 180, it will be a lot to process, multiplied for every frame. So how it will work in this case? As you can see here, we have a distributed file system, a queuing system, a set of APIs. So let's imagine like in Florence and SAM, there are 2 different models. So they're deployed on 2 different services. The first one will be fetching the video clip, process it, store it again, plus storing, for example, the detections. So you can have the bounding box or you can have the dense region. And then when you send the completion, starts the next one, that is reactive system. So in the reactive system, you will then see all the data moving until then at the end, you send just a signal back to the client, say, okay, your video has been annotated here, so you can download it, or for example, fetch here the checkpoints that I've just downloaded for you. Okay, so why Florence? Florence, as you might know, is a unified prompt-based model that performs a variety of computer vision tasks. So we can say that is a multimodal language model. So it accepts both text input and images or set of images. In case of, for example, simple tasks, caption, detailed caption, and more detailed caption, this task basically accepts the image and is able to understand what is in the picture. So if you, for example, send an image of a park with the 3 people walking in front of you, Florence would be able to say 3 people walking in a park. Or you can say more detail, 3 people, 1 wearing a hat, 1 wearing jeans, are walking in a park during autumn because maybe notice that the leaves are yellow, and so on. So then you have OD, object detection, dense region caption, and region proposal. As you can see, the output format change. So you can have bounding boxes in case of this task that I mentioned, plain text, but at the same time, you can also set OCR and caption to phrase grounding. OCR, as you may know, is used for identify characters in a photo. Simple application of it, you want to scan your passport. For example, if you fly with Ryanair, they allow you sometimes to scan your credit card to get the numbers or to take a photo of your passport, and then automatically they fetch the data from it and they populate your persona. This is basically done via your OCR. OCR with the region is similar. At the same time, it also identifies what is the boundary around it. And I left it for the last because this one is the task that surprised me the most. It's caption to phrase grounding. So as I said, Florence accepts both text and image. So what if we put everything in an iterative approach? So caption to phrase grounding allows you to give a caption, an image, and to retrieve bounding boxes on top of it. So imagine if you want to give a detailed output, instead of making Florence assume that maybe that is what you are expecting, you use caption to phrase grounding. So in this case, for example, returning to the one I said before, you say, there is a man walking in a park. In this case, Florence will directly give you just the bounding box of the man, and maybe can give you also the park if, for example, the image has also other things that is not a park or a man. So it just exclude everything that you didn't put in the face grounding. And as you can see from the diagram on top, this is how you can put it in a use case. So you can have surveillance camera, and you can, and maybe you're expecting that only your dog is walking in the house. So you put in the phrase grounding, a man in a house, or a woman in a kitchen, a woman in a corridor. So you can put it as a phrase grounding, and then if the camera see that something that match your grounding is identified, send an alert, for example. That can be a generic use case. Or you can say, passing the videos, say, verify that this every 3 frames, there is the dog on the couch. If it change, because you didn't find it, in this case, you can apply it to the security camera to send, for example, an email. Okay, identified limitations. So as I presented it, Florence might look like really great tool. You can perform a lot of different things, is accurate and so on. Well, there are always some side of the coins. So I mentioned caption to phrase grounding is the one that surprised me the most. Well, it can also create hallucinations. We have to keep in mind, and this one is also in common with SAM, we need to keep in mind that these models are trained on a really huge data set. So it can be biased. It can be biased by the training set and the input. So in this case, for example, the 3 people walking in the park. It can be that instead of being 3 people, Florence return man, man, woman. And maybe there is a person that from the back looked like a woman, but is a man. And this person, for example, doesn't want to be identified as a man or a woman. So in this case, the data set can be biased and can produce result that if you use blindly can make a lack of accuracy. At the same time, there is also another problem. If you put 3 people in a park, but there is just the image with the park and 3 people without anything else, there can be a possibility that your model return the full picture as a bounding box. And you don't need that. If you have a series of pipelines where you're using this as a tracking, that can cause some noise in your data set. So as I mentioned now, tracking. Florence does not allow you to track objects. For Florence, even if you pass 100 frames, 200 frames, 500 frames, maybe you have NVIDIA 100, so you can put a really big bulk of frames, Florence doesn't care. It's still 1 frame per processing. So you can even say, give me these 3 people and track them for all the set of videos. Doesn't care. There are still 3 people. There are 3 different unique elements. And it can be that if you want to force it to have a tracking, they are 1, 2, 3 in 1 frame. 3 frames later are 3 to 1. So under this point of view, you cannot be sure only with Florence to have the same object that is tracked for the whole video clip. So you can, of course, combine it with different products. It's ready to be done, but you cannot do it out of the box. And main challenge in our topic, small objects. Florence, unfortunately, reshape all the images to 1024 to 1034. So what happened? If you're watching a football match, you have most of the time 16:9. Imagine that this photo now is getting squeezed horizontally and also reshaped to 1024. You might lose a lot of detail. So you cannot just plainly using Florence in order to cover this case. You need to combine it with, for example, slicing of the photo, slice and overlaps. There are different techniques on top of that. But out of the box, this can be a risk. So you have to keep it in mind if you want to make, for example, some surveillance or some factory or industry checks. For example, if you want to track some supply chain. So this is really important use case. Confidence level. I guess like who work with the computer vision heard at least once about, for example, YOLO. So usually YOLO provide you a confidence level of each object in order then to choose if you want this object to be picked or not. For confidence level in Florence is not provided yet. So there is a community on top of it that is talking with Microsoft, open a lot of tasks on top of it, a lot of issues. But right now, it cannot. Because for Florence, it's enough that I'm doing all this set of tasks. If I can provide also the accuracy on top of it, my model will be really confusing. So they claim it that right now, they would rather have yes or no instead of yes, maybe a bit so, maybe a bit more, no. And detection loss of perspective. This one, in case of the motorbikes video, is one point where Florence identified maybe 30% of the time the motorbike. For the other 70% did not. Or it found, for example, the wheel only, or the rider, or the helmet of the rider. So, or there was a moment that even from the back, Florence gave me horse. So you cannot rely 100% on that because, as I said, the topic and the data set is getting changed multiple times. And for who discovered AI and deep learning models only after ChatGPT had the boom, Florence-2 doesn't allow follow-up questions. So if you ask forest, 3 people walking, and then it identify only one, you cannot reply back to Florence and say, hey, I'd say that there are 3 people, not only one. You cannot. So it just one prompt, one image, one answer. Okay. So why SAM? Here it comes. So for who is familiar with old school video games, this is serious SAM. So SAM-2 is not that serious, but still is seriously strong. So where SAM-2 jump in? SAM-2, as I said, is a segmentation model. So when you pass a set of bounding boxes, like for example, gun, rifle, pants, it can then extract the shape of the object from the bounding box. But this is something that sometimes is required, but sometimes not. So how SAM helps in tracking? So SAM is the first model that is unified for segmenting not only photos, but also videos. So as you can see here in the right, there is a memory bank. So memory bank is the main core of the video tracking. So how SAM works, basically when you give a set of points or bounding boxes, it stores the perspective of the object in memory in order then to reprocess it, and every time you use what you passed as an input, as enhancement to the next step. So as you can see, you can pass a user prompt, so it can be manual. So you can, for example, stream the video clip in live and allow the user to put the point, or you can delegate a grounding model, like Florence in this case, to do half of the job for it. So at the end of the day, you can just recreate the model, recreate the video with the annotation, or you can just use the detections that have been provided. As I said, images and videos are supported, but nowadays you need also streaming. So streaming capabilities is not yet supported by SAM. There is maybe I counted like 15 or 16 forks from the same library where people are trying to apply the streaming capabilities. Some of them work, some of them even made the paper and say, we did it, but is not officially released by Meta. So you can use it for your experimentation. You can do it in order to perform some checks on top of it, or even just to comment on their code and say like, nope, you're wrong. But you cannot use it for production. Okay, so let's consider now this example. As you can see, the motorbike is tracked for all the time. So we didn't lose the point even once, even when the motorbike was changing the perspective. If we check it with Florence, Florence would maybe lose it like, take it like one image every 2-3 seconds. Because at the beginning it's horizontal, perfect, identified, but then it lost it completely. Okay, but how it solved the problem with tracking? So this is a video of actually my team's football team here. And you can see I'm using Florence to track the ball. In the triangle, you can see that the ball is identified, then disappeared, then identified, then disappeared. In some cases, even started to be completely lost. So it followed, but see, even when it's clear, you can say, oh, damn it, how is it possible? It found out when it was far, but it could not see it when it was closer. Simple illumination. So, and the other point here, I didn't use any slicing technique. I just put the whole video and I say, process it. Let's see what you can do. So how SAM-2 is helping me with the tracking? As you can see, here I'm doing exactly what I put in the previous diagram. So you can be the user that select the point, or I can take the same results that I have from the previous video, and for every time the ball is found, I just put it in a memory bank. Memory bank of SAM works with input prompt. So you just pass the bounding box and say, this needs to be accepted. You can also pass the opposite. So if, for example, Florence confused the ball with a penalty disc, in that case, if Florence found this detection, you can then take this detection and pass it to Sam and say, like, this has to be excluded. The ball, no, take it, but the disc, no, exclude it. Or the middle field, when in the middle of the middle field, you say, okay, you confused it, you thought that was a ball. This is not a ball. So you can mark it with the label 0 or 1, depending if you want to have it as yes or no. And at the end of the day, what I do, triggering SAM predict video, it just creates new object predictions and fill the gaps that Florence had across the video clip. So how this is performed. As you can see, it will be really like short amount of code of lines. So here we initiate SAM. What we do here, we initiate a video predictor where I pass the model name. Here is not hard-coded because model name can be of 4 different variants. So you can have tiny, small, base plus, and large. If you have a really big virtual machine, at least a Tesla with 15 giga of VRAM, you can perform the large, but the video clip needs to be at least resized. With the full HD, might go out of memory. If you have an A100, you can do it perfectly. There is no limitation. Or if you have a multi-node VM, perfect. But in most of the time, tiny or small is perfectly fine, especially for edge devices. Then you have to store the video as a series of JPEG or PNG images. And then you create this inference state. So inference state tracks all the points as I mentioned before. So it will be loading frame, prompt, frame, prompt, frame, prompt, and load it in the VM, in the VRAM. And you can choose, if you, for example, have not big VM, if you are pretty short in terms of resources, you can either offload the detections on the CPU, or you can even offload the state. So instead of using everything from the NVIDIA RAM or the NVIDIA AMD, from, let's say, the CUDA memory, you can just put something that you're not going to use on the disk or on the server RAM instead of having it in memory. Then, as I said, you add the points. So here, what you're getting, we use supervision library. I hope that you guys know about it. It's one of the most important open source libraries used as a utility and also for serving computer vision models, and is done by RoboFlow. So using supervision, we get the anchor coordinates. So what is it? Imagine that you have a bounding box. You can decide to take just the coordinate at exact middle of the box, or top right, top left, bottom, depending. In my case, I'm taking the center of it. I make it as a list, and I pass it to the prompt for every frame that I have a detection. So at the end, what I have is series of points, a series of masks of the objects that I already identified, and nothing for everything that was not found. Then I do predicting video. So here you can see that we have a response where in the response, what we have every frame that was not placed as a prompt. So if you have 900 frames video, so 30 seconds video clip, 30 seconds for 30 frames per second. And you put 30% of these identifications. The other 60% is directly calculated by SAM. Like for example, in the video for the motorbikes, I just put like one every 100 frames. And at the end, you can see that the motorbike was never lost. So at the end, what you do, you fetch everything, you generate the masks for the specific object ID, and you just create all the masks on top of it. And how you integrate it with Florence? We create a Florence task. We give an input, for example, locate this object in the image, motorbike. So at the end, Florence tried to find the motorbikes. In that video, there were two. But if you noticed, one was not tracked because I added an object ID for that specific bounding box, and I exclude everything else. In this way, when you pass it to SAM, I have exactly those frames with those IDs to be tracked. And in fact, here I pass SAM model inference state for 5. 5 is my frame ID. And I decide to say true or false if I want to include it or not. And I trigger basically the predicting video that is fulfilling the gaps. So the video about the match was, as you can see, now the ball was lacking a lot of frames. And here is the result after Florence and SAM. So as you can see, the ball is always been tracked, even when it's in the air. And we can see that in some cases, when the ball is hidden between a person, it might get confused. But this one was run on a model that, first of all, is not fine-trained, is on the full HD with slices. And you see the ball got tracked for like 99% of the time. So moving forward, here is maybe more clear the difference between what was with only Florence, what was with Florence and SAM. So on the left, we can see with the 720 pixel resolution, on the right with 1080. With 720, you can see that on the top left, a lot of frames were missed. So in blue, you can see the frames that have been missed. In white, where there was the identification. On the left, data frame SAM, you can see how many frames were not tracked by SAM. There is one point here to be considered. If the object is hidden or is covered by something else, obviously SAM doesn't say that it found the object. So identification is 0. So this can happen when, for example, during the video, there were like the person that was receiving the ball and the ball was between the camera and, the person was between the camera and the ball. In that case, was 0. But look at the difference in terms of loss. And in the bottom, you can see it, the distribution per seconds. So if you miss one frame, it's not that critical, but just take a look at per second. So when you have 100, is basically when SAM found the object. In blue is Florence. So there is even a moment that Florence was close to 0 for multiple seconds, while SAM never went under 80% of identification per second. So now here we are considering one really complex scenario because low leagues football, of course, don't have the same professional cameras as professional teams have. So you don't have, for example, the high overview, bird view, the camera is moving, is not stable, and so on. But in this case, you can see that the light was the main issue that SAM was not scared about at all. Florence, definitely yes. Okay, but SAM seems that the resolution of these problems, but what is the other side of the coin? Real time, as I mentioned, you cannot perform streaming on video clips. Hopefully there will be soon this feature. Meta is really active on the SAM library, especially because it's used also in the MetaQuest. So in MetaQuest, they use SAM to identify the objects when you are in full mode with the holograms. So like also Apple Depth Pro that is used in our case. In my case, we use it in order to check how far the ball or the goal is from the camera. So in this case, SAM is used by Meta in order to identify the object. If you now wear your MetaQuest and you want to go to Horizon, you can see the Christmas tree and it can create an hologram on top of it that is generated by AI. But in order to create that, it needs to segment this object. Everything is done using SAM. So this is something that right now works with images, but is not accurate for tracking. I guess SAM will be also with the streaming capabilities provided directly by Meta in the next future. Same as Florence, there is biasness. As I said before, it can be that what identifies something, can be that is identifying something with a different name or different classification. The same thing is for SAM. So in case of SAM, you can, for example, pass a really convoluted image, like, I don't know, people in the crowdness. In that case, it can be identifying a shape that is maybe not one single object, but is, for example, an accumulation of multiple objects. And we said, oh, this apple is actually too close to another object that looks like an apple, and altogether can make, for example, a big apple. It can happen. Or is trained for this image of this type of tomatoes that look like two connected to each other. It can be that this image is segmented in that way. So you need to consider a lot of these scenarios. User prompts is still one important point, because if you need to track video clips, SAM still needs this prompt to identify the object in order then to add the tracking capabilities. So you can use grounding, yes, but what if the grounding is not enough? Like Florence, in my case, was covering more or less 30% of the ball. But if I want to reach a really good accuracy, like excluding something that looks similar but is not what I want, in that case, I still need to go to the video, check where is the moment where I want to exclude the penalty disk, and remove it. One crucial point is the one in the bottom, crowdness. As I mentioned, crowdness is where the SAM can get confused, because you can have the same object that it can look similar to another object of the same shape, the same type in a video clip. If you go to the same website, you can see that there is a video with multiple horses that look similar because they're horses. They're all horses. They're all the same color. And it's one horse disappear, then reappear again, and this horse was considered another one. So, or it happened that it was another horse that looks similar, but had a different color, and in Sam's mind was the same object. So in this case, Sam can lose some level of accuracy. Or if, for example, you consider a camera taken from the top for a car, from the top, a lot of cars look similar. So imagine if you put the camera on a highway, you might have one car that is identified, then suddenly confused with another one. And then you cannot, for example, track the speed limit. And in this case, you cannot use it for considering if someone is going too fast towards the camera. Because if I have a car that is the same as another one, maybe this other car is going too fast and think that is mine, and I can get the ticket. So it's something that needs to be considered under this point of view. And the other point, this is more for beginners, for people that are just facing SAM for the first time. Documentation is, in my opinion, quite bad. So you can go, you can check the Python code, the Python docs, but it gives you samples. So if you want then to go deeper in these scenarios, well, good luck, because you have to try on your own. So debug can be quite expensive, especially if you want to have something self-hosted or use some VM that you're paying on cloud. Well, it's going to give you a lot of pain. So especially if you want to tweak some parameters, or you want to have some model, some bounding box that have to be shaped and excluded in some other cases, you need to understand that. And in order to go over it, it might take a lot of time. The other point is memory usage. As I said before, the goal of these two products were to be used on a lightweight way. So they were supposed to be used for edge devices and so on. But if you want a high level of accuracy using SAM-large, you need a huge amount of VM, huge amount of RAM, especially the memory RAM. And in some cases, even if you have an 80 gig VRAM, it's better to partition the video in multiple pieces and process it in bulks. It all depends on the cases, but if you, for example, in my case, during the video of the football matches, I was processing 5 seconds, 10 seconds per time in order to have always at least few object detections per bulk. Because at the end, if you stream a live match, people don't even notice if you are 5 seconds in late or 10 seconds late. They just are interested in the match. So in that case, 10 seconds delay, it's a buffer that you can consider as accuracy price. So yeah, but at the same time, you need to consider it. And the other point is, if you want to fine tune SAM, you need the 2 nodes VM if you want to fine tune the large, because the minimum that Meta is suggesting is 90 gig of VRAM. So an A100 doesn't fit the model. Okay, we jump to a conclusion about it. So can we consider them as a sword and shield? On one side, Florence. What is positive? What has been great from the beginning? It's competitive solution. It literally take few lines of code to just deploy them, even using Hugging Face, and you can just serve it. It's really ready to use. It's fast forward, and you can even use it for multiple tasks. It's really lightweight. So as you can see, the large model is 0.77. So it can easily run on CPU as well. So it's something that it give a lot of points to Florence. And on the other end is one model for multiple tasks. So even if you want to create your simple Android apps or iOS app where you scan some documents and send them forward, it can run on top of it. It's really light. And you can perform OCR, you can perform object detection, and so on. And it's really easy to integrate. The output of Florence is always a dictionary that is easy to understand, and you can pass it forward to other pipelines without going through tensors of tensors of tensors of tensors. So you just get the dictionary back and you can send it forward. Negative, like any lightweight model, needs fine-tuning. So in my case, I didn't use it because ball, person, field, it's something that is in a lot of datasets. You don't need the specific fine-tuning. But imagine it if you want to use it for documents or orders, like someone receive a ticket, a bill, or they go to macro, buy the bill and say, okay, but now I need it as a JSON because I want to pass it to my API where I keep tracking all my expenses. In this case, you need the fine tuning because Florence doesn't even know what is a JSON, but it can interpret an image, give you a result. You can apply some customization on top of it, but at the same time, it doesn't give you anything out of the box. Or if you want to apply it to your factory. So you produce something innovative, something that has your own shape, your color, whatever, you need to fine tuning. And the fine tune of Florence require a lot of time. So even if you have a pretty big VM, The fine-tuning is pretty straightforward, but you need to consider all the LLMOps or MLOps practices that you have to put on top of it. And yeah, caption to phrase grounding, I mentioned it before. I will not gonna spend a lot of time on top of it, but as I said, it generates hallucinations. So if you want to have object detection, just use object detection. Don't use caption to phrase grounding. Caption to phrase grounding can be used only if you want to enhance a prompt on top of it. Because on caption to phrase grounding, you can pass another box, for example, that was previously calculated. So you can use it as graduator or as I said, next step in the evaluation, but not out of the box. And as I said, struggle to say small objects of the same type. So in that is something that, for example, if you use slices, sometimes can be confusing. The ball was identified as moon because it took just a corner where there was the ball and was moon. So you have to consider also these usability issues on top of it. SAM, in my opinion, tracking an object without fine tuning is great. Under this is really great. Never been so accurate. The API, as I said, if you go just now on Git, download the library, you start to using it, perfect. It's really straightforward. Few lines of code and you're on top of it. Okay, but if you have to do it to something specific, it's going to make you stay sitting on your chair for hours to understand what is happening under the hood. The feature of video tracking is mind-blowing. I suggest you all to try it out because even for simple, even the change of the angle that they show also on their website, and I personally experience it. If you take the one object, like I tried with the with Premier League during a Chelsea match, I selected Palmer, and then after a while the camera changed. Was on the first was from the back of the goal. The object was still tracked. So even if it changed the side, still the object is identified and is tracking the same object ID. So when you receive the response from SAM, you have mask, logits, object ID, and frame. The object ID never changed, so was still found as the same one. And on the other hand, there is a lightweight that is not so light as expected. So you can use Tiny for images, simple images like clothing is perfect, works really good. Videos don't go under the base plus because it loses a lot of accuracy. Prompt management, as I said, is not straightforward. So even just this add to prompt with the bounding box, or if I want to put a point, or if I want to include or exclude, no one tells on the documentation what is the best in which scenario. So why should I use bounding box instead of a point like a frame? That is something that you need to find out on your own, because on the documentation, they just say you can pass this one or you can pass that one. That's it. The memory is getting overhead. So if you put too many prompts, imagine that every time you say to SAM, add this box to this frame, it generates a block in your VRAM that is the size, sorry, the size of the matrix is basically the frame. And then it's applies some post computation on top of it that goes straight to your VRAM. So if you have 900 frames video clip and you want to add 700 or 600 points, all these 6 points are 600 independent tensors. So it's something that you need to keep in consideration, because maybe it makes sense in some cases to just pass 1 point every dot frames. That is one thing that I did in my case with motorbikes, because at that time I didn't have the possibility to use a big GPU. So I just put 1 point whenever I had the possibility every 100 frames. And at the end, you can see that there were no lack of identifications. And what else? Yeah, as I said, streaming is still crucial in some scenarios. We don't have it yet. And the biases. you can still fine-tune SAM, but it will take you nights. So you need, first of all, to create the data sets. And I don't know if you guys played in the past to creating data sets for segmentations. It's really painful. Take a lot of time. You need to use platforms that, even if you use RoboFlow, that is paid, by the way, to do this, it takes a lot of time to just take the image, make a segmentation, move it forward, or you can use some other tools to ground the image, then create a data set, and then you train. So in some cases, you need to be really cautious if you say, okay, I'm going to take SAM and I'm going to fine tune it. Just think twice before jumping into it. Okay, here are 3 projects that I used in my case. They are publicly available on GitHub. They are basically unpacking already your Florence, SAM, and I added also Depth Pro because I don't know if you guys are familiar with Depth Pro, but is a library that I'm using right now in our videos and in cases with motorbikes, with ball, where it tracks and identify the distance of an object from the camera. So it can make a prediction of, actually I can show a video for that. Let me see if I can go over it. It should be this one. Okay, no. I don't think I have it, but no. No, I don't have it. I think I have it in the repositories. Okay, so I was saying that depth, it can allows you to have a prediction of the focal length of the lens that in most of the models for predicting distance is the most crucial one. So you cannot know how much the lens is zooming, what is the spectrum of it. Depth Pro is really accurate in guessing it, but you can also pass the focal length if you are already aware of it, and it calculates the exact distance from an object that you want to track to the camera. So in our case, for the video with football match, we know that we use VEO technologies with this camera that can just track the ball and keep it always in the middle of the camera. But sometimes, of course, doesn't work perfectly. That's why it came this idea with my team to work with that. And in that case, the depth, I checked with the camera passing, okay, I know that the depth of this camera is this, it can work with this setting, and the distance was perfect. So with the camera put on the middle line, exactly on the line, and the ball next to the corner kick on the other side was saying that is 72 meters. That is, it's like 73.8 is the exact distance on the pitch that was that time, but 72 point something, 73.5 or 0.4 doesn't really matter if you consider that at the end you have all the field to be analyzed. So if the ball is straight to the corner or a little bit far from it, doesn't change that much. And on these repos, you can build, you can have both the reference to the Docker image that you can download directly from my repository, or you can build your own one. So feel free to jump on it. It's pretty raw version, so you can just install it and start with it. It uses Fast API on top of it, so you can just pass the image, get the results, processing after that. But yeah, feel free to also provide feedbacks on the GitHub repos. And okay, the moment that our guest waited for long, so Q&A. Okay, let's see if there is someone online first.
I don't see yet. So, okay. We have one question.
Is it possible to fill in the missing frames with some kind of prediction where the ball should be? Yes. So this is something I tried. For example, I tried to predict the next position of the ball when the ball was not identified. And I gave a set of potential prompts to be identified as true. And it didn't end really well, because if you pass the point, and this point maybe just target the pitch or the field or the void, like the sky, in that case, you're just creating noise in your data set. But yeah, you can still try, Bogusław. Okay. Any other question from online?
Not yet.
Okay.
I think we can check in offline audience.
Okay. Anyone from offline have some questions? Yeah, sure.
First of all, thank you for the great presentation. My name is Jalil, and I would like to ask about this SAM. As you know that for specific use cases, we need to fine tune it. So could you please tell me about like at least how long video we will need to have like high accuracy for specific cases, and like as you said, it's gonna take a long time for training, but like what kind of machines we will need to train this model? Thanks.
I reply first the last part because it's the part I get. So what type of machines you need is, first of all, depending on which model you want to fine tune. So for the tiny one, even the simple Tesla T4, so the 15 gig is perfectly fine, and it's fast. Also depends on the dataset size. So if you want to train it with big images, small images, if you have like millions of prompts to analyze or not. But in general, with the tiny, you don't need that big computation. If you are going to the large, consider that the original training of SAM was run on 10H100. So 10H100 is like, I think more than 1,000 giga. So it's pretty huge. Of course, for fine tuning, you don't need such capacity, but yeah, it's something to consider. Like A100, I think, is the minimum to train the SAM large. And I didn't get the other question. The video for fine tuning. Sorry, I still don't get. Okay. So how long it took to create a data set? So for example, consider that the base one is slightly bigger than Coco dataset. So the base model is based on that, plus a model that is based on Meta dataset. Of course, Meta, like they did with Llama, sometimes they release the datasets, sometimes they don't. In terms of SAM, in order to find a proper dataset, you cannot predict it. So if it can be like a simple scenario, like you want to check some supply chain for products that are easy to recognize, you just want to train it if, for example, an orange is spoiled or not. So in that case, you can even just take the original image, add some green mark, let's say, from different perspective, and then you can use that as a data set. For more cases like motorbike, football, and so on, as I said, you cannot, because you need to consider, for example, the football player or the ball in different perspective, different color, different light. You need to maybe consider one part of the body, the other part of the body, and still mark it as person, for example. So this is something that it's unpredictable, especially if you want to use it to some specific case. Like you want to identify all the players from Liverpool. You know that they are all playing in red, so you can fine tune the model to work only with the red team. But what if one day Liverpool decided to become green with kit? In that case, you need to go back and do everything from scratch. Any other questions? Yeah, sure.
Thanks for the okay, thank you for the presentation. So I have two quick questions, right? So when it comes to train the model, we have two types of data set, like big data set and a small or data set, right? So in this case, how many rounds we need to train our model to get the best accurate model for testing the model? For both of them, is there any standard, or like we need to try our best to get the best accuracy for those model when we train them? And also, like, is it different for the large data set and the small one when it came to this training this model for both of them? It's both deep learning.
Oh, okay. So I would reply to you in steps. So first of all, like big data set, small data set, you always need big data set. So even if there are some cases where you want to track, as I said, oranges, you need to have the data set under a lot of different perspective, different distance, different angle, and so on. So we are always in a scale of big data set, especially if you want to reduce the model to work with your data. So if you want to avoid noise coming from other type of models. The other point is about accuracy. There are different principles that you need to follow when it comes to training. So you need to consider the precision, you need to consider the data loss, the recall. There are multiple metrics that you have to consider. So you cannot be sure that you need, for example, 300 iterations or 500 iterations or 100 iterations. In some cases, you prefer maybe to have a model that is less accurate, but at the same time is not overfitted, instead of the opposite. So it's on you making the training and evaluation to find the proper boundary. Because if you make your data set to be always true, as I said before, like you train the model to have Liverpool team and everything is always with red, 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 your model is overfitted. So in the moment that you pass something that is the different color, it's not going to work anymore. Did I cover your question? So,
We
for
have
example,
questions in the chat.
Okay. For Florence, for example, I trained one model just for sorry, just for the ball, especially when it comes to, I said, low leagues football, where this camera is not high. So the perspective is always different, especially because sometimes we can have the possibility to put the camera a little bit higher. Sometimes we have to put it just on the side of the field, so it's like 3.5 meters or so. But in some cases, we can have it even at 10 meters. So in some cases, I needed to iterate, maybe I think it was like 600 or 800 epochs in order to have a good level of accuracy. So yeah, it's unpredictable. SAM, I tried, and the morning after I have to turn off the VM because I noticed that the billing was already at $3,000. So if I didn't want to get fired, I had to stop the VM. Okay, I see. I got one from the chat. Do you think models are suitable for identification human body moves, like hands are crossed, legs are crossed? As far as I know, they don't. They cannot identify the posture. But I need to check on the SAM. Sorry, on the Florence usability. As far as I remember, no, Florence does not track the posture. At the same time, you cannot use it to identify key points of an object. For SAM, it doesn't matter. SAM still tracks the shape of the object. So legs crossed or hands closed, the eyes, and so on. they are getting a part of the same bundle. So if you just identify the hands, you put the point on the hands will be tracked, and it's then on you to understand if the hands are open, the hands are closed, they're moving right to left, left to right, and so on. I hope I replied to you. Okay, is it possible to recognize on video really small object like balls with nuts? Thanks. Yes, SAM under this point of view is really great. It was perfectly possible to track really small objects. There is also a fine-tuned version of SAM, is called SAM URAI. And this one is a fine-tune that optimize also the memory bank, where you can track an object that is smaller and is getting a lot of crowd noise. So yes, the short answer is yes. Okay, let me go a little bit. Is it possible to place here in comments the 3 places on the GitHub of your presentation? Yes, of course. So let me, okay. And what else we have? In the missing frame is okay. This one we answered. Is it possible to run a SAM-2 inference on a video clip or stream or images on a Segment25 tops NVIDIA edge devices? I didn't try, so I cannot give you the full answer. But at the same time, streaming, as I said, streaming capabilities is still not yet supported natively by SAM. So yeah, you can perform it with images anyway, even if it's not possible to run it on GPU based, you can still run it on CPU. And by the way, it works perfectly fine even if you have MacBook with metal processing accelerator. So you can use also MPS. Okay, so we have, can we track motion of fast moving objects with high resolution and continuous smooth motions of frames? That is actually the best option. So the best scenario is when you have really high resolution and continuous smooth motion. So this is like the perfect scenario where if the models don't perform well, it means that something is wrong, or on the prompt or on the image itself. So in some cases, it can happen that you need to change, for example, the channel of the image, change the color, or exclude some objects. For example, in my case, for the ball, I used also CLIP to just exclude something that was around the ball and just put as a negative. So if, for example, there was the player that was behind the ball, I was using CLIP to just identify the box and doing basically A minus B. So I was taking the box and then I was excluding the points where there was the ball and track it as negative. So in this case, I was able to, for example, exclude something that can make the noise. But in general, high resolution, if you have the hardware, perfect. And you can also perform really well predictions. If, for example, the video works with 120 frames per second or 200 frames per second, SAM get the more prompts you give, the better works, but at the same time, yeah, at a higher cost. So in that case, with, for example, a sport camera that can process 120, it's the best for tracking purpose. Okay, so any other questions from the audience online? Yeah. Is the video frame rate as relevant as video resolution? Which one has a bigger effect? So both video resolution and frame rate are all going to the memory bank. So if I come back here on the diagram, so imagine that every frame here is a matrix in your memory bank. So the more frames you load, the more you're using the memory. At the same time, the frame, the image resolution define the size of the matrix. So at the end, even if you have to consider the result, so in some cases, it's better to resize the image to have, for example, a scale ratio of 0.5, 0.75. It depends what kind of ratio you want to keep, because then it's not only the processing, so the input to the model, you need also to work with the result of it. So imagine that then for every frame that has been returned with the mask, you have in memory a matrix of, for example, 1120 times 1080 for every frame. So if you load it in your laptop, it will basically make your system crash. So yeah, they are all, like say, we like with the fine tuning, also the serving is something that is really important. So for example, if I go on GitHub for the SAM, so here in the app, when I serve the model, instead of returning the whole matrix as a result, okay, so predict video. So here, instead of returning the whole matrix, what I do, I basically take all the points that the mask as true. So instead of returning 1920 times 180 of true, false, true, false, true, false, I just say 225, 991 is true. All the others are false because we don't care about the false. So at the end, we need only the true. And the true is, in this way, the result, so the returning JSON is time slimmer. So in this way, you can have also the pipeline to work. Like in this case, it's working with the streaming of the answer. So every frame then will give me the result with the mask that I can consume in my app. The only thing that you need to wait is the initiation of the process. Then your app can work with stream, but the video must be loaded fully at the beginning. So in this way, you can, as I said, you can deal with the limitation that are hardware and software. Do you think that, or maybe even tried, current movement of the player could be used as a part of the prediction for the movement position of the ball? In our case, as I said, the camera was already doing majority of our work. So the camera was already moving and tracking the object in order to keep it most of the time relatively in the middle. That actually is also useful because I could have exclude identification of, for example, the ball that was not the one that I was interested in. So if, for example, there was a ball next to the corner kick, I could have excluded it because I expect to be in the middle. But in that case, if I have to use it for considering the current movement, that's actually why I was using Depth Pro. So I integrated with Depth Pro because I can see how the player is moving across a series of video clips. So if I see that the distance from the camera is changing and I'm noticing that the object is moving from left to right, in that case, I can understand also if the player is moving diagonally or if it's moving straight line or is moving vertically. Because if it's vertically, most probably the object didn't move the focus at all from the camera, but is just changing the distance. So in this case, it's just getting longer. And if then we plan to have a 2D radar, I can basically show the movement. The same thing can be done with the ball, but at the same time, the ball is moving in 3 dimensions. So while the player, the worst case, can jump 2 meters, if it's Cristiano Ronaldo, 2 meters and 70, but the ball can even move up in the sky for 10, 15 meters. So in that case, how hard it will become to consider where is on the field if, for example, the distance, even if it's high from the camera, is considered 100 meters or 20 meters or 80 meters. So this is something that for prediction of the movement needs it's really, really, really important. For some cases where the camera is stable and the object is just moving from left to right, in that case, it's not even required. Okay, so I think that's it. I will give the word to you for closing.
Okay, thank you. Simon, thank you very much for your presentation. Thanks everyone for joining. We will be sharing the recording. So I wish you a good evening and thank you very much.